So I just thought it'd be a good idea to put up on one piece of paper here. Just
hang on, it's just starting. Yeah. Okay, so now for Jim's third lecture.
Okay, yeah, thank you. So I thought it would be a good idea to, since the last lecture was a little abstract, and maybe to just kind of review some of the key points to consolidate it. So I'm just kind of listing them here, maybe in, I don't know, the enumerations maybe not so important. So the Witt vectors, which remember were this infinite product, and the delta shifts the components, and the ring structure is defined by some exotic polynomials. They're kind of more conceptually thought of as this this co-induced delta ring.
Sorry, I'm sorry. Recording needs to be started. Raghavan has pointed out.
Yeah. It's being live streamed on YouTube, so that should take care of.
Okay. Yeah. Yeah. Sorry. Yeah.
Okay. I don't need to restart or anything. And then, so if this ring is this ring of the so-called p differential operators, which is it's actually, maybe I should have written this here. It's isomorphic to a polynomial ring on infinitely many generators. And these generators are these right here. And then, so when you take homomorphisms from this polynomial ring homomorphisms from this polynomial ring to A, you can say where the generators go arbitrarily, and then you get an infinite product. And secondly, in fact, any free generating set, which will be countable, induces such a bijection. So the approach that we took was, when this free generating set was the iterates of the deltas, this was our definition of the vectors, but there's another, of course, there are many canonical generating sets. You can, add one to all of the generators and you get a different canonical generating set. But there's another one which is most traditional. This is the standard one. And these are these elements theta n defined recursively by this. So the iterates of phi were, remember, phi itself, the first iterate of phi was the pth power map plus p times delta, and so on. So these are all these iterates of phi are in this ring of p differential operators, and one defines the thetas recursively like this. And then the theorem is that, first of all, the thetas don't have p's in the denominator, and secondly, that they're also a free generating set for this infinitely generated algebra. So so then, if you see here in number 3, this was the bijection we started with. So we had some exotic ring structure on this. So corresponds to the ring structure on this. This is a ring isomorphism. Using these so-called Witt generators, we have a different bijection, and this is the standard one. But they're both isomorphic. And the ring structure here is the one coming from this. So they're both isomorphic to this kind of abstract Witt vector construction. But so they're isomorphic to each other, and it's on the first two components, it's the identity. But once you get to the component number 2, the third of the components, it starts to be a bit non-trivial, and then presumably ever after it will be defined by some non-trivial polynomials. But this is an isomorphism. It's a canonical isomorphism between these two rings. However, I just really think of it as this kind of abstract thing. So the point of the last lecture, which maybe I kind of rushed this point, it could have been put off to the 3rd or 4th lecture, but I wanted to emphasize that there are these two definitions, the one I gave in the first lecture, and then there's the traditional definition. But the difference between them is only because in one case you choose one generating set, a different one, another case you choose another generating set, but they're just kind of generating sets that describe the same abstract algebra of these p differential operators. In much the same way, if you have a module, you have an algebra and you have a basis for the algebra. If you look at a co-induced module for that algebra, you can describe it concretely using the basis for your algebra. But if you have a different basis for the algebra, then you'll get a different concrete description. But sometimes one concrete description is advantageous, other times another one is. But one shouldn't make such a big deal about the difference between them. So I guess I want to emphasize this because often it's a bit confusing why you would have such crazy polynomials, but it just is kind of an artifact of some two natural generating sets. Yeah, so that was the topic. That's a quick review of the last. It's what the point of the last lecture was, just to kind of make contact between the approach I described, the definition of vectors I described, and the definition you'll read in basically everywhere in the literature, with one or two exceptions. Okay, so now we can go to the main topic of this, start this lecture proper. So section 5 on finite length. Although if there are any questions on the before I start, something a little different. If there are any questions, I'm happy to entertain them. Okay, so right, so the usual Witt vectors, we had, remember the product, A goes from 0 to infinity, and this is, so one, I'm kind of abusing notation here. There are different coordinate systems one can choose on the Witt vectors, but what I mean here is just the delta coordinates, the one that I started. And then one can truncate these vectors. We can take a product from 0 to n, just like this, and let me call this Wn of A, and I haven't told you the map. Of course, it's just truncation. Let me write it out explicitly. So it sends an infinite length vector to this. So one warning is that our Wn of A is most people's Wn plus 1 of A. So W0 of A is A. I have strong opinions that this is the right way to index them. I could give you all sorts of reasons why, but it's not the traditional way. So I just want to emphasize that to everybody. So when most people talk about W2, that is what I would call W1. Okay, but now the point is, this is obviously surjective. And the point is that the ring structure, so it's a set quotient, the ring, but it's also a ring quotient. The ring structure on WA descends uniquely, of course, to 1 on Wn of A. And the proof, remember, what is the ring structure here is given by these Leibniz rules for addition and multiplication with respect to the iterates of the delta operator. And so proof, the Leibniz rules, which I was calling Pn plus and Pn times for the nth iterate of delta with respect to addition and multiplication depend only on the previous, let me write it this way. Only on lower iterates of the delta operator evaluated at the arguments. Maybe I should say, let me put it this way. Leibniz rules for delta n of x plus y and delta n of x times. So just like the usual Leibniz rule for differentiation, the derivative of a product depends only on the 0th and the 1st derivatives of the two arguments. It doesn't depend on the 7th derivative of either of the arguments. And because the polynomials expressing these Leibniz rules are precisely the polynomials defining the addition and multiplication law on these Witt vectors, so at the nth component, that polynomial never refers to the n plus 1st components, simply because these Leibniz rules depend only on the derivatives up to order n. Okay, so this is the ring of length n Witt vectors, truncated. Just a few obvious things. The ring of infinite length Witt vectors is just the projective limit of the finite length ones. If you like, since just because that's true of products. These truncations are not delta rings. There is a delta operator if you like, but remember the delta operator just shifts components to the left. So you can shift the components, but you lose one length. So you have a well-defined operator like this. So the delta operator on the infinite length Witt vectors descends to 1 on the finite length Witt vectors, but it changes the length. And similarly, Frobenius does the same thing. If you like, Frobenius of x is just kind of formally, it's this, and so there is, maybe I should say, there's a of course there's just the obvious projection. The delta is a shift, but you can also just project. Let me call that rho. It just sends a0 up to an to a0 an minus 1 and this one sends that to a1 up to an, and then we kind of think of rho as really just being kind of the obvious projection, kind of almost the identity map. So then the Frobenius is just kind of the obvious projection plus p times this. And then this will be a ring homomorphism. Okay, if you like, you could say that, maybe I'll say that, delta is a p derivation. I didn't just talk about what a p derivation would be if you change the ring, but because this, you have just a regular ring homomorphism. Oh, this is a ring homomorphism. Maybe I should say that. Okay. Also a ring homomorphism. So you could say delta is a p derivation with respect to the ring map rho. So I could have defined more generally a p derivation with respect to any ring homomorphism, but in the first lecture, I just did it with respect to the identity map. Okay, so let me, one thing I haven't done yet, maybe I was a little amiss in not talking about this. Let me just give a concrete example, which probably many people know. the finite length Witt vectors, when evaluated at FP, the field with P elements, are uniquely isomorphic to the integers mod P to the n plus 1. There's the shift that maybe is not familiar to some people. And then in the infinite length case, of course, the infinite length Witt vectors are the, as I wrote up here, the projective limit of the other one. So the infinite length Witt vectors are then uniquely isomorphic to the p-adics. So let me prove this, and I'll prove it from this delta point of view that I've introduced. Right. So so what do we have? We have the integers mapped to FP. We're going to use the universal property. And then remember that, well, okay, there's a unique lift. Of course, W is just a ring, of course, so there's a unique map from Z to any ring, in particular W of FP, but we know what that does. We know how to say what the map is. It sends an integer A to, you take the vector of all the, so Z is a delta ring, right? Remember, delta of A is this Fermat quotient, A minus A to the P on P. And what do we do to this universal property of the Witt vectors? Says we apply all the iterates of delta to A, and we get an infinite length of an infinite sequence of elements of Z, and then we just project them to FP. So I'll say A bar is just A modulo P, and then we can take delta of A and then bar of that, and then delta composed with delta of A and bar of that, and so on. So that's what the map is. But it's actually quite easy to say what it is, so more precisely. So suppose we write A is P to the M U, where P does not divide U. So assuming A is non-zero, you can write it this way. And then the key point is that, so here's the key computation, delta of P to the M U. What is this? Well, it's just this Fermat quotient, right? So it's P to the M U minus P to the M U to the P divided by P. So this is P to the M minus 1 times U times 1 minus what? P to the, what did I do? I factored out of M, so P to the M times P minus 1 times U to the P minus 1. I think that's right. U to the right. So, right, so what is this? This is just P to the M minus 1 U. So assuming M is non-zero, so at least one power of P divides A, then this will be a higher order p-adic term. So so these are higher order terms. So we can just write it like this. Okay, so this is why you might think of, right, this is Boollium likes to think of the delta operator as differentiating with respect to the prime number P, which is a little silly in some ways, but really there's a lot of good reasons to think of it that way. And so you see, it kind of decreases the order of vanishing at P by 1. Right, so then we can just continue. And so if we take the ith derivative of P to the mu, this is P to the m minus I times u plus higher order terms. So therefore, under this map here, our element A, which we're writing as P to the mu, what will that go to? It will go to the reduction mod P of all of these elements. So at first it starts off, they're assuming M is at least 1 or something, you'll get 0, and then you get a bunch of zeros. And then as soon as I becomes equal to M, then you just get U, and then you get the reduction of U modulo P. And then after that, who knows what you get. And how many times do we have to do this? We had to do it M times. And of course, U bar, I've assumed U does not divide, P does not divide U, so U bar is not equal to 0. So therefore, the kernel, you can now see exactly what the kernel of the map from Z to W and P is. It's any, so in W, that it will, well, I'll just tell you, it's P to the n plus 1 Z. So as long as you have, if M is at least, remember in Wn, we have M plus 1 components. So maybe I could say here, these are components numbered 0 up to M minus 1. So then the, if you want the mth component to also be 0, then M in Wn, if you want, sorry, if you want the nth component to be 0, then M has to be at least M plus 1. Okay, so then that that finishes the proof. I guess it's quite easy to see it's surjective. So I'll just say QED. Let me say one more comment. So more generally, maybe I should be honest and put some dots in there. More generally, if R is a complete discrete valuation ring, which is absolutely unramified, so the maximal ideal is generated by P, and the residue field is perfect, residue field K is perfect, then Wn of K is the same as isomorphic to R modulo P to the n plus 1R. Okay, so now I'm about to use this to make these jet spaces in the Greenberg transform, but maybe I'll pause to see if to answer any questions if anyone has them.
Yes, I have a question. So
yes.
Something I was so for the K I agree, but I'm looking at just the ZP and FP T mod T square. So what happens with these cases? If I take Z mod P square Z, then its Witt ring will be again ZP, right? That is, if I take Z.
Okay, so wait, hold on. I'm not, let me make sure. So your question is, you take the Witt vectors of Z mod P squared Z.
Yes.
No, this, this will be, this will be ZP direct sum a big square zero ideal.
Square zero ideal of
in itself. So it will be a module. M is a module, and then M becomes a square zero ideal. So it will, okay, so what, actually I'm going to talk a little bit about this example. So you have W of Z mod P squared Z, this maps onto W of FP, just by functoriality. And the kernel will be all the Witt vectors whose components are multiples of P. So sometimes people write this, even though it's a ring without unity, so it's a bit of an abuse, but they kind of write it this way. And then in fact, this that surjection is split And this ideal here is a square zero ideal. But this ideal here it's uncountable. It's an infinite product of copies as an abelian group, or as a, well, it's actually true as an abelian. In fact, yeah, I'll talk about this stuff. This is it's isomorphic to an infinite direct product, 0 to infinity, of copies of FP as a group. So the conclusion. So this will be later. I'll justify this later. The conclusion is that W of Z modulo P squared Z is isomorphic to ZP direct sum, this big product, and this is square zero.
So parallelly, I have another question. I mean, just because I'm comparing two situations now with Z mod P square Z, instead of that, if I look at FPT mod T square, and I look at the Witt vectors of that ring,
yeah,
will you have the same situation again? I mean, there it's like rings also split in some sense.
Yeah, I think that is, I'm pretty sure that's right. I think the same argument up here will apply here. And so I think amazingly, these two are isomorphic. And I believe, let me hedge myself, I believe that this is isomorphic to W of Z mod P squared Z.
So just asking another question, like generalizing this, because I'll be interested again in R. So if it is, will it be same thing if one does it for Z mod PRZ and FPT mod TR? Like you look at the Witt ring.
I think not. I think so. Yeah. So I have this certain point of view, which is goes under the phrase of the field with one element. And from that point of view, if you take a ring and view it over the field with one element, what that means is that you take the Witt vectors of the ring, and you can't forget the delta structure. Mm-hmm. But so the conclusion is that that Z mod P, and I think this is true. This is true even as delta rings, if I remember. This isomorphism, I believe. It's been many years since I thought about this. So then the idea would be that these are isomorphic over F1, which is kind of what you want. And I was happy when I discovered that, but I believe this fails once you get beyond 2. So I also believe that W of FPT, it's conceivably could be true up to T cubed, but I'm not sure. Let me, call that R. Let me just hedge my bets and, not for, I'll just say for R large.
So there is something more that happens with the rings in general, like one has to know about ring, again for the Witt rings and all, right? In the
What do you mean one has to know about rings?
In the sense that, I mean, okay, I don't know. I thought that when we started with that, maybe there will be a direct connection in the Witt ring of these two rings. Somehow I was hoping for that. Okay.
Yeah, I can, yeah, why don't you hold that thought and we can, so next time I wanted to talk about actually, because I want to talk about Lie algebras of these jet spaces, and then exactly these kinds of things will come up. So so we can talk about this more. Oh, by the way, in your previous question about the topology, you see here that this is, so the Witt ring for this reason, these would be discrete, typically understood as being discrete, but then then this one will be pro-discrete. So it just, you can't usually just think of it as having the product topology, but the free objects, the free delta rings, they're infinitely generated, but they're still discrete. Okay, are there other questions?
And one more silly question. I don't know. I mean, I couldn't figure it out. So what is the Witt ring of a Witt ring? So if I take ZP and I ask, what is the Witt ring of ZP? What would that?
That's good. You're asking all these good questions. So, okay, so here's an exercise for you. So here's the two. So one is W of ZP is this is a subring of an infinite product ring, so it's isomorphic to the set. Now this is I write them with angle brackets for some reason. So this is now the product ring. So the ring operations are defined component-wise. It's the set of such ones such that x to the n plus 1 is congruent to x to the n modulo p to the n plus 1 for all n. So it's these things are p-adic Cauchy sequences of a certain kind. They converge at a very specific rate. So that's and then the ring operations are just component-wise. So this is obviously this is not, these are not the usual components because the ring operations are component-wise. So to define this isomorphism, you have to say something.
Is delta just the shift?
No, let's see. So then Frobenius is the shift. Shift left. And then delta is, well, delta is, so what is delta? Delta of a vector x0 is, what is it? It's just the, it's the pth power map. So the pth power map is now defined component-wise, minus the Frobenius, and the Frobenius I told you is the shift divided by p. So this is then equal, and the operations are component-wise. So it's x0 to the p minus x1 on p, comma x1 to the p minus x2 to p. And because now you might think that this is another way, another approach to defining the Witt vectors. So you see that the components here are all p-adic integers still, because each of the x's, any two consecutive x's are congruent modulo p. So these will all be p-adic integers. But recall, to be in here, you need more than that. You need not just that they're p-adic integers, but you need these two. For instance, the first two components, right? Just like here, the first two components have to be congruent, not mod p. Now these two components have to be congruent mod p. And for that to be true, you also need these two components here to be congruent mod p squared, which is why you need them to keep being more and more congruent. So let me tell you, the question in general is that, so if A is a delta ring, in particular a Witt vector ring, then W of A is, I think I need to assume p torsion free. then W of A is it's almost the same thing. In once again the infinite product ring, but now now xn plus 1 has to be congruent to the Frobenius of xn mod p to the n plus 1. So that's what that's the answer. Those are exercises, not super easy. Of course, there's nothing profound here, but in principle, it's an exercise you could assign to a first year algebra class, but it wouldn't be so easy. Yeah. Okay. There are many more things one could say about that. Okay, so now let me talk about arithmetic jet spaces, which are also called Greenberg transforms. Some people use the two terms slightly differently, but we won't worry about that. Okay, so first, let me just say a little bit more about Witt vectors of finite length. Wn of A, right, was the product. In fact, it's inequality equal 0 to n A, and then this is in bijection with the ring homomorphisms from something else, which I'll call delta A, where now delta n is just, it's the same as delta, but you stop adjoining generators when you get up to the nth one. So this is just a polynomial ring on n plus 1 algebraically independent variables. So when you take homomorphisms to A, you get n copies of A. And so this so this delta n is contained, not equal to delta, which was, remember, polynomials when we don't stop. And these are we could call these the operators of order at most n. And there's an analogous free construction. So what you can do something similar with linear operators. Then the analogous situation for linear operators might be like delta is a polynomial ring in one variable, and it has a filtration by degree. So now we're doing kind of a filtration by order, and instead of the things of order at most n being in the linear setting, it would be a direct sum of, degree 0, degree 1, degree 2, and so on. Now we're taking a so that you'd have a basis, a linear basis of the powers of x if you're doing polynomials in one variable. In this case, you don't have a linear basis; you have algebraically independent generators. So free generators in the sense of ring theory, not in the sense of vector space theory. And then we define a finite length analog of this construction I told you before, and it's just the same thing, but you truncate. You only go up to level n. So we have generators which are symbols like this. So I is now at most n, and A is an element of A. And then we have the same relation. So okay, I want to get to the arithmetic jet spaces, but maybe I'll give you one more exercise. So you can show that delta n circle the integers modulo p to the n plus m plus n z is uniquely isomorphic to so unlike Witt vectors kind of make you closer to characteristic zero, these things kind of take you further away from characteristic zero. Okay, so now the arithmetic jet spaces. So let's set x. Let x be a scheme. So you should think a scheme over the integers, just any scheme, but an affine scheme is great, or an algebraic group. So e.g. SLN over the integers. Then one can always think of a scheme as a functor by its functor of points. So this is a functor from rings to sets, which just sends an input ring R to its set of R-valued points, which is just by definition the set of homomorphisms from the spectrum of R to X. So, for instance, for SLN, maybe I won't use n because I'm using n for the length. SLD, for SLD, it just sends a ring to actually SLD of that ring. So it's a fantastic notation. Oh, okay, so now we define, here's the definition of the arithmetic jet space. Maybe many of you can guess it already. Jn of x is a functor, and it's just the composition of x with the Witt vector functor. So we have rings, that's the Witt vector functor, and rings to sets is x, and then this composition is Jn of x. So in other words, the R points of the nth jet space are just the points of the usual, the scheme you started with, but with coordinates in the Witt vectors of the ring in question. So for instance, say we take Jn of SLD of Fp, right? This is just SLD of the nth Witt vectors of Fp, which are of course the integers modulo p to the n plus 1, according to the normalization in these lectures. So one can compare this with the usual jet spaces. I'll call it Jn usual of a variety x, when evaluated at a ring R, is just x of the truncated power series. And so, for instance, one way of defining the tangent bundle of a scheme is to do exactly this construction when n equals 1. So J1 usual of x is the tangent bundle.
Sorry, I'm a little confused.
Yes. Please.
So firstly, two questions. So the first question is, so is the point of this definition that the composition of X with Wn itself is a scheme?
Yeah, okay, exactly. So that was exactly my next point.
Okay. The other question is, what is Jn usual? I think I missed that.
It's exactly this. It's if you've seen just geometric jet spaces, maybe usual is maybe we should call it geometry.
Okay.
if you've seen any, algebraic geometers will study jet spaces of varieties and things like that, and motivic integration, things like this, and they're defined exactly this way. So it's if you like.
So would this be the differential analog?
Yes. The only with one caveat, and that's that before I was taking divided power series. So if you're in characteristic 0, though, the difference between power series with n factorial in the denominator and all power series is there's no difference. So yes.
I'd just like to take X circle W diff. Would that?
Yeah, no, yeah. So okay, so that's good. So we could define J and diff of X of R, but then this would be X of what I called W and diff of R. But recall these are divided power series. These are the set of things of the form a to the n, t to the n on n factorial. N is the a to the I, t to the I factorial. I less than or equal to n. So then we could also define, so it's a little different. So if X is in characteristic 0, so if it's a Q scheme, then this issue of denominators, like here denominators are allowed, up here denominators weren't allowed in the series. So then J and diff X will be the same as J and geom X. The difference is have you heard of something called Hasse-Schmidt derivations? So a Hasse-Schmidt derivation is it's a system of things that formally behave as the nth derivative divided by n factorial. So if you just want one derivation, which is what I used in my first lecture, then the Witt vector construction that you use is this one. But if you allow yourself a whole family of derivations that behave as the nth derivative mod, they're not only the first one's an actual derivation, but a whole family of operators that behave as the nth derivative divided by n factorial, then the notion of Witt vectors you would get is exactly this. But normally people just look at these things in characteristic 0. Although that's not true, I guess. Pooja, all you guys look at truncated power series in characteristic P. But at least the papers in algebraic geometry and so on look at these things in characteristic 0, and then the two constructions are equal.
Thanks.
That would be an interesting thing to look at the group theory. Question, what is, SLD of W diff n of FP? This is some other truncated thing. It should be similar. So we have, what is this? So this compares to SLD of the usual Witt vectors, and then SLD of FP T modulo T to the n plus 1. It's kind of a third alternative.
Oh, I thought there was nothing else.
But in length 1, if length 2, if n is 1, and so the difference will only come up, the difference between this construction here and this construction only comes up when n is equal to p, or maybe p minus 1 or something like that. So since the smallest prime is 2, if you don't see it yet, but in the stuff that Pooja has written about.
Okay.
Yeah, okay. So here's a question. So is the functor J and X scheme, if X is, I guess I said, let me, so the answer is yes, but let me say, I'll say an affine scheme if X is. And the answer is yes. And in fact, it's easy to say what it is. The nth jet space of the spectrum of a ring A is in fact the same thing as the spectrum of this other construction. So what's the proof? Proof, I mean, it's basically kind of nearly a tautology once you unpack all the definitions. So what I claim is that, so homomorphism, so what we have to do is, okay, we'll look at the R points. So this right here is the R points of this. It's just the ring homomorphisms from this to this. And what I claim is that's really the same thing as the ring homomorphisms from A to Wn of R. Let me, maybe I'm being a bit too quick on this. So this is, these are the maps from spec R to spec A. Those two sets are in bijection. And these are the maps from the spec of Wn of R, spec A. And this right here is precisely the R points of this scheme. And then this right here is precisely the R points of that scheme by definition. Remember, the R points of this thing are precisely these homomorphisms. And so we just need to, our question is whether those two are the same. And I claim they are basically exactly by the definition of all these things. So if you had such a homomorphism in here, remember what was this thing? It had generators like this and then a bunch of relations. And what homomorphism do we send it to? We send it to the homomorphism, which sends an element A to a Witt vector. And what Witt vector is that? It's the Witt vector where in the ith component, it's gamma of delta of I of A. So remember the generators, the generators here are this. So you can take any symbol of this form and evaluate gamma at it, and you get an element of R. So this is a vector of elements of R. In other words, it's a Witt vector. And then, so that gives you a perfectly well-defined map from this set to this set. And the fact that this is, well, you need to check that this is a ring homomorphism here, but it is that somehow it's exactly, everything's defined in such a way to make it kind of tautologically a ring homomorphism. So these two sets are then in bijection, and then that finishes the proof. So you might have to ponder that, but I claim that there's no real argument. It's just, you just unpack all the definitions and then they're just the same thing. Okay, so why don't we do an example? Although maybe, let me, the example I want to do is just J1 of SL2. But I can pause for questions if there are any. Okay, so what is it? It's just the set of 2 by 2 matrices with determinant 1 with entries in Witt vectors, with entries in W1. So, okay, let me just write it out. So J1 of SL2 of R is by definition SL2 of W1R. So what is that? It's a set of matrices of this form, such that the determinant is 1. And so this determinant is computed in Witt vectors. And 1 in the Witt vectors is that vector, 1, 0. So now we can just work this out. So what I'm doing is doing this example in kind of just straight from the definitions without trying to do anything clever, just unpacking everything. So what is this equation? Let's call this equation star here. So what is star? The left-hand side, well, you have to remember how to multiply Witt vectors. A0, P0, and A0 to the P, P1 plus A1, P0 to the P, plus P, A1, D1. And then we subtract. Let me actually, what I prefer to do is move this term here to the other side of the equation. So I'll expand it on the other side, D0, C0, P0 to the P, C1, plus P1, C0 to P, P1, C1, plus 1, 1, 0. And then what is this? So now how do you add Witt vectors? You, in the first component, you just add them naively. And then in the next component, you first add them naively. And then we have this sum with binomial coefficients, remember? So then it's 1 on P choose I. But then it's, yeah, what is it? It's running out of room. It's the powers of that component and the powers of that component. So this one here is a 1, so we don't need to worry about it. So we get B0, C0 to the power I. So that's the equation. So now this is an equation between 2 Witt vectors. So there are 2 components, so it means each of the pairs are equal. So therefore, the defining equation is equivalent to the following pair of equations. So the first one is A0 is this equals this, which is just the usual determinant equation. That's the part, if you like, of the Witt vectors of length 0, which are just usual numbers. And then in the next component, I'll just write it down. But I'm not going to really add anything to it. Don't have anything to say about it. So 1 to P minus 1. Okay, so those are 2 equations. So therefore, J1 SL2 is a closed subscheme of 8-dimensional affine space over the integers. 8 because you have 4 variables with zeros and then 4 variables with ones. defined by two equations. So you'd expect it to be 6-dimensional, and it is. So another way of thinking about this, suppose, so this was not using, there's this observation I had here in the computation I just did. I didn't use that observation. I just expanded it straight from the definition way back up here, this definition. But alternatively, I could have just, I mean, it's going to be the same thing, but I'll just say what it is. Equivalently, we could have just computed delta 1 circle the usual coordinate ring of SL2. And then this would be equal to, so the way, when I define this construction, I think I maybe mentioned this last time, when you write down the generators, you only have to, it's enough to just use any set of generators you like. So let me just, you'll see what I mean. So those are the generators, and then we have the original relation, and then we apply delta to the original relation. But by this, I'll put quotation marks around it, because by this, what I mean is you have to expand that using the delta rules to become a polynomial in these 8 variables here. But once you expand everything out using the Leibniz rules, it will become a big polynomial in 8 variables. And which polynomial will it be? Well, it will be this polynomial right here. So now down here, I'm using different names for the variables. Up here, I had A0, B0, C0, D0, and A1, B1, C1, D1. Down here, I'm just using A, B, C, D, and then delta A, delta B, delta C, delta D. But it's going to be the same computation. Okay, so that's how you determine the arithmetic jet space of something. Maybe we can push this example a little bit. So there's a homomorphism. Okay, should I say, I mean, maybe now's a good time to say it. So Jn of G, say G is an algebraic group, evaluated at R is G of Wn of R. And this is a group, right? It's just, it's the value of an algebraic group at a Witt vector ring. So therefore, G an algebraic group implies that Jn of G is an algebraic group. Say over Z. So we might try to understand what this is as an algebraic group. I mean, that's kind of the whole point of at least how kind of the advertisement for these lectures, that if you remember, you want to understand, say, SL2 of Z mod P to the n plus 1Z, it's a nice finite group, but we want to think of it as an algebraic group. So that's what we're doing. So, right, so we have J1 of SL2. There's a group homomorphism. We could think of this one as J0 if you like. That's just SL2. And what that does, it just sends, it's just the truncation map on the coordinate, on the rings in whose coordinates you're looking. So right, A0, A1, B0, B1, C0, C1, B0, D1 will map to just A0, B0, C0, D0. So on yeah, on FP points, it would be integers mod P squared, mapping to integers mod P. And this will be surjective. I mean, assuming your algebraic group is smooth, which will basically always be true unless you maybe have some exotic p-adic examples. So that will be smooth. That will be surjective. So we can ask ourselves, what is the kernel? Well, it's not that hard to determine. So what is it? It's just the set of matrices, which it's a set of matrices like this, which reduce to the identity matrix. So the A0 and B0 are both 1, B0 and C0 are both 0. And then we can even just kind of take that out. So let me write it this way. It's just the identity matrix 1 plus the set of matrices like this, such that determinant is 1. So this is now a subvariety. Now we have four variables. We have four variables, A, B, C, D, and so now this will be a subvariety of affine four-dimensional space and defined by one equation. So what is well, technically it's an equation between Witt vectors, but the first component is kind of tautological. So what is the equation? It's 1a times 1b minus 0b times 0c equals 1 comma 0. It's the same equation as before. So this becomes the equation 1, and then so this is sorry, getting this wrong. It's a plus d plus p a b minus 0, and then how do you multiply this? This just becomes p b c. This should be 1 comma 0. So that's the same thing as maybe I'll do it as I did before. It's a little easier to add Witt vectors if one of them is simple. So this then becomes and one nice thing actually about Witt vectors when you could like, maybe I should have mentioned this earlier. You can think of the addition law for Witt vectors as being like carrying in just in school arithmetic. When you write z mod p squared is like fp cross fp, you have two p-adic digits. And when you add, it doesn't just go component by component. One component influences the next component. So it's kind of like carrying. It's kind of it's like a functorial way of talking about carrying in p-adic arithmetic. Yeah, so if we have these zeros here, there's no carry. So you just get this, and then the first coordinate is obviously satisfied. So this is, you just have one equation, and the equation becomes a plus d plus p a d equals pbc. But now let me subtract. So this is so the kernel is closed subscheme of four-dimensional affine space over the integers defined by one equation, which is this one. One thing that's worth pointing out is that, so this is as an algebraic group over Z. If you're only interested in kind of things like this, and things like this. Remember, this was the value of a jet space at FP. So you might say, okay, Witt vectors of rings and characteristic 0, that's all nice and fun, but what I really care about is Witt vectors of rings and characteristic P. I'm going to argue that you shouldn't think that way, but suppose you did. I'm not going to argue that now. Maybe I'll argue that later this lecture, maybe next lecture. Suppose you did, well, then you would just want to determine, so you might ask the question, what is, if you, this is an algebraic group over Z, but now if you just take the base change to FP, this is an algebraic group over FP, and if we only want to know the FP or FQ points of this jet space, then we only need to know that algebraic group. We don't need to worry about what it is in characteristic 0. Then you see that, right, the kernel, the equation defining the kernel, so let's call this star star, then star star is just a plus b equals 0. So the kernel in characteristic P, the kernel over FP is just SL2, the algebraic group SL2. So what do we get? We get extension. So this is over FP. That should be, so that's over FP, over FP, over FP. So that's what the arithmetic jet space looks like in. So we have to be a little careful. We start with an algebraic group over Z, or it could have just been the integers modulo P squared. That would have been enough, but it's not enough to just start with the integers modulo P. And we take this first jet space, we get another algebraic group over, well, if we started over Z, it will be over Z. If we started with integers modulo P squared, it will be an algebraic group over FP. But then we look at the fiber over P, and this breaks up in that way. So it's an exercise to show that the action is the Frobenius twisted adjoint action. So if you want to prove that, you just have to write down your matrices like this, and then I mean, I guess there's a conceptual way of proving it, but you can just give a straightforward way where you just conjugate some matrix in the kernel by some general matrix, and then you just see what happens. Okay, perhaps it's time for a question. No? Okay. So that was just an example. So let me step back a minute and say a word about computations. So just what I did, we can write down, so J1 X, say X is a scheme, or it could be an algebraic group, whatever you like, is not so hard to write down. I just did it. Write down explicitly. And because the Witt vectors of because W1 of R is not so hard. And the reason is just because these Leibniz rules for the delta operator are not hard. I mean, they're not so simple, but you can write them down with some binomial coefficients and things like that. Once you get to higher length, then you're going to be in trouble. There's going to be, as I like to say, I don't think anyone in history has ever written down these Leibniz rules when n equals 2. So question, how can we compute with J and G, I'll say for an algebraic group, when n is bigger than 1. So what I'd like to do, and I'll just barely get started this time, and I'll finish it next time. So here's an example. What is the Lie algebra of Jn SL2? And let me, I'd like to actually talk about both. So I'll put a base. Well, okay. I'll do FP, but in fact, the answer will be more interesting if I allow the base here to be arbitrary. So for any algebra K. But kind of in particular, the case where, well, K equals Z will be the main case. So intuitively, the idea is, what is, so this is a, this will be, this is a group scheme over K, right? You take the Lie algebra, then you'll get a vector space over K module. So this is a K module, and it will be finite. It's quite easy to see that this is defined by finitely many equations and finitely many variables. So this K module will be finitely generated. So it's a finitely generated K module. And I think it's kind of fun to write this. And you could kind of think of the idea being, if you take K is to be FP, and then that's like looking at the SL2 of the Witt vectors of FP. So it's sort of saying, intuitively, what is this as an FP vector space? That's kind of the idea. So so you'll see now we get to Pooja's question from before.
Sorry,
yes.
I'm a bit, so are we talking about this as a group scheme, and then it's Lie algebra and the algebraic geometry sort of setting?
Exactly.
Okay.
Yeah. This is nonsense what I've written here.
No, but up above, yeah.
Up above, exactly.
Okay.
Here, that's right. JLN, it's a group scheme. It's a variety, if you like, and we're just computing the tangent space. It's a variety over K. Yeah, so Jn of SL2K is a variety, in fact, an algebraic group over K. And in fact, the defining equations, I kind of meant that's, if we go back up here, this right here, if you want to compute the defining equations, what you do is you just take the initial defining equation, which is this one, and then you apply all the iterates of delta to that. You get a mess, but you'll have, at least in principle, it's a computable list of defining equations. Right, so how does one compute a tangent space in algebraic geometry? You use the dual numbers. So what is that? so we have this exact sequence, Jn of SL2 of K epsilon mod epsilon squared. That maps to Jn SL2 K. And then the kernel, this is surjective. Again, because these algebraic group, if the original group or the original variety is smooth, then the jet spaces will also be smooth. Maybe I should have said that. In fact, it's also true for schemes. So if X is a scheme, then Jn of X is a scheme, and if X is smooth, that implies Jn of X smooth. So these algebraic groups would be smooth algebraic groups if the one we start with it. And then, so then the kernel of this map is exactly the Lie algebra of the tangent space. Maybe this, I guess, it'd be as a scheme. Like this. So this now is SL2 of the length and Witt vectors of K epsilon mod epsilon squared. And this, of course, is just SL2 of the length Witt vectors of K. And then the kernel is what we want. But to determine this kernel, you kind of have to be able to understand what that thinks. So the Witt vectors of some ring with a nilpotent element, it's a little, you know, it's say K is a finite field, then this is something maybe people understand. It's just the integers modulo p to the n+1. But this is something more complicated, and it's the kind of rings that Pooja was asking about in the beginning of the lecture. So, so the question I want to talk about next time to answer this question. So, how do we compute in Wn K epsilon squared? Or more generally, if you want to do a computation in Witt vectors of length n, a specific computation, okay, so here's answer one, is you determine the Leibniz rules for all the delta operators up to delta n. And then those will be some giant polynomials, and you can do whatever computation you want using those polynomials. That's basically how I did it in the first case we did. The polynomials are small enough when n equals 1 that I even have them, by now I have them memorized, and I can just do that. But this is completely unrealistic if n is bigger than 1. And the point is somehow determining those polynomials would tell you how to do computations in Witt vectors of any ring whatsoever. But we just have some very specific ring. And we can economize a lot by taking a different approach, which is what we'll do. And so what you want to do is you want to lift the ring in question, which in our case is this sort of thing, to characteristic 0. Now, if K itself is of characteristic 0, it might already be in characteristic 0, in which case you don't have anything to do. But if K is Fp, then a nice thing to lift it to would be, say, the dual numbers over the integers or over the p-adics or something like this. And then you then you perform the computation there. So we might lift it to something like this ring, if FP, so if K is FP. And when I say characteristic 0, I mean P torsion free is what I really mean. And so now you perform whatever computation you want to do there, computation there. And the key point is this is much easier in characteristic 0. So Witt vectors, people most often apply them to rings in characteristic P, but if you remember, they're really born in characteristic 0. They're defined using this whole Frobenius lift business, which is something that you can really only make sense of in characteristic 0. And therefore, anything you ever prove about the Witt vectors has to go through the definition, and the definition happens in characteristic 0. Unless you're using a theorem that somebody else proved, but then they would have had to do that. But that has actually implications for doing computations. So you perform the computation there, which is it's much easier because it's in characteristic 0, and then you reduce back to K epsilon mod epsilon squared. So what I'd like to do next time is just show you, I'd like to illustrate this, so we'll do this to compute the Lie algebra of Jn of SL2. And I think it will, but what's the purpose? The purpose is I think it might be just interesting because maybe the people in this attending maybe have some interest in algebraic groups and things like that, jet spaces of algebraic groups. But also, I think it will illustrate this principle that basically to prove anything about Witt vectors, the best way to do it, even if you're interested in Witt vectors of things in characteristic P, is it's basically always to go through characteristic 0. And I think you'll see kind of a nice illustration of that when we do this. Okay, I think it's about time to stop. Happy to try to answer any questions.
Here by lift, you mean you look for a ring that projects onto this ring? Like
yes,
when you say
yes.
project.
Yeah. I mean, one thing you could do is you could take the Witt vectors itself of that thing, but it sometimes that doesn't help you, but you want to take some approximation maybe. But you can, the wonderful thing is you can take whichever, so the point is that, so say you have R tilde is a lift of R, then W of R tilde still surjects onto W of R. So if you have a computation you want to perform here, say you want to add two Witt vectors together, what you can do is you can just lift them individually to here. And then if R tilde is a nice enough ring, like I gave you some examples in the beginning of the lecture with these congruence conditions. It's not so hard to do a computation in such a ring. So you then perform the computation here, and then you reduce back to that. But the wonderful thing is that it doesn't, I mean, that's just somehow obvious. It's obvious that that will work just because of the functoriality of the Witt vector construction. And in particular, it's independent of whichever choices you make. So you should choose whichever makes your job easiest.
So I have one question here about the Lie algebra. The way you're defining it like a kernel of this map, right? So
yes.
Is this a defining? Like, I mean,
I guess you said, is it a scheme?
Huh.
Is that, yeah, no, I'm being a little sloppy, I guess. I guess this will be isomorphic to some affine space over K. And then, I mean, it'll be the affine space corresponding to a vector space. So, so more properly, Lie of, I guess Lie of any algebraic group G would be, you take the scheme and then you take its K points, where I think this is how it works. I'm not an expert on these things, where Lie G is the kernel of Lie GK. Wait, what did I sorry. No, I actually, so these, I'm being a little sloppy. So these, we've evaluated at a K. So this is a group, in fact, a finite group. This is also a finite group. And then this, no, this is exactly right. So this is the layout. So this is, so I was here evaluating at a particular K. So yeah, this is a finite group. This is a finite group. This is also a finite group. It'll be, if K is, say, a finite field, it's a discrete. What I should have said, it's a discrete. This is a discrete group. This is a discrete group. This is also a discrete group. But if we had, if I had not evaluated and left it as this, which is just a scheme, and then Jn of but then I would have had to, so this is, it's kind of funny because this is also a geometric jet space. So that would be J1 geom of Jn of SL2. So we're kind of iterating those things. And then the kernel would be the scheme theoretic Lie of Jn of SL2.
Okay, now I see that why that K epsilon by epsilon square was, okay, interesting.
Yeah, I think it's just the tangent space. It is a little, so the connection with differential jet spaces is, I don't know, I guess it's a real thing, because one could look at higher order ones where you get these germs. Yeah, so let me, so this is let me get rid of this.
Okay. Yeah, very interesting. We need to work on this over the week.
More exercises also we
Yeah.
No problem. Okay.
Okay, thanks, Jim.
All right. Thank you,
See you
everyone.
next week.